Hello children, welcome back to the channel. Today we'll be starting up the very important topic of angular momentum as promised in my previous video. So what is angular momentum? Now to understand this, first let's consider a rigid body rotating about, say, the origin in the counterclockwise direction, and let's consider one particular particle of it which is located at point P. So since the body as a whole is moving, the particle is also moving with the rigid body, right? When it is moving in the circular motion, the particle P, which is traversing certain circular path around the origin, right? Something like this. So due to this, it will have a momentum, linear momentum, a velocity vector tangential to the path, and since it has a velocity, it will have a momentum also. Let's say the particle has a mass of m and velocity of v, so it will have a momentum p, which is equal to mass into velocity at that particular instant. Okay. Now, if we extend this, the momentum vector or equivalently the velocity vector in the backward direction, and drop a perpendicular from origin. Origin is the point about which it is moving, so the z-axis will be our axis of rotation. So from the axis of rotation, if we drop a perpendicular to the direction of the momentum, linear momentum, or direction of velocity, and let's call this length be d. So by definition, angular momentum is nothing but moment of linear momentum, which means in magnitude angular momentum which is given by L, capital L vector. So magnitude of angular momentum will be the magnitude of linear momentum multiplied by the perpendicular distance between the axis of rotation and the angular momentum vector, extended or whatever way. Okay. So moment of linear momentum of a particle executing circular motion will be known as the angular momentum of the particle. Okay. So if it is so, then the dimension of angular momentum will be dimension of momentum multiplied by dimension of length, right? D is length. So if we look at this, what we have, momentum is m1, L1, T inverse, and length is L. So this will be m1 L square T inverse 2, which again give us the unit of angular momentum. What will be the unit of angular momentum? In SI it will be kg meter square per second. In CGS it will be gram centimeter square per second. However, kg meter per second can be written as kg meter square per second square into second. Now this gives us the unit of kg meter square per second square is the unit of work or energy. So we can rewrite this as joule second. Right. Similarly, from this we can also say it is arc second. So angular momentum is sometimes expressed in terms of kg meter square per second, sometimes it's expressed in terms of joule second, both meaning the same unit. Okay. So now if we consider this particular diagram here, and we already have given that L equal to P into D. Now let's consider this term to this point to be M, say. Now let us say the position vector of P is given by the vector R. which means if we extend this angle theta will give us the direction between the momentum vector and the radius vector, right? So we can always resolve the momentum vector into two components. One is radial component, the other one is the tangential component. The radial component will be along the radius vector, which will be P cos theta, and this will be the perpendicular component will be P sin theta. This will call P radial, and this we will call P theta, that is P tangential. Okay. Now let's first consider the triangle OMP, which is a right angle triangle, M being the right angle, right? And also this angle will be theta, right? Opposite angles. If this is theta, this has to be theta. So from the geometry of it, what we can say is that D, that is perpendicular by R in magnitude, perpendicular by hypotenuse, will give us sin theta, or D will be equal to R sin theta. If we substitute this value of D into the equation of angular momentum, that is moment of linear momentum, what we will get? L must be equal to P R sin theta, or we can also say R into P sin theta. Okay, from here let's take two different roots. First, Rp sin theta is equal to vector R cross P modulus of that, right? Or we can say angular momentum, just as we were able to express torque in a vector term, angular momentum is R cross P. So it is the cross product of linear momentum with the radius vector. Okay. Alright. Now, if we continue from here, let's say L equal to P R sin theta, right? This is one part of it. The vectorially how we can express L we have found. Second is that if we say consider two special cases, one is theta equal to 0 degree or 180 degree. What do we mean by theta equal to 0 degree? Theta is 0 degree means P vector will be along the R vector, which means P will be parallel to R vector, or it will be going radially outwards. Momentum will be going radially outwards. Theta equal to 180 degree means P will be opposite to R vector, which means it will be coming radially inwards towards the center. In either case, this expression will give us L equal to 0, because cos sin 180 degree, 180 degree or sin 0, both are 0, which means for a particle moving radially outwards or radially inwards, the angular momentum will be 0. So there will not be any rotational or angular part component of the momentum. Second is that if we consider theta equal to 90 degree, then L will be R into P, which will be its maximum value for given R and given P, because sin theta will be 1, which is the maximum value of sin theta. What it means is that when L is L is 90 degree, or when theta is 90 degree, theta is 90 degree when the particle is executing circular motion around the given axis. So what it means is that when a particle is executing circular motion, or when a residual is executing circular motion about a given axis, then the angular momentum has the maximum value. Okay, and if it is moving radially outwards, it will have 0 value. And if the P vector is making some other angle, like here the path is like this, it is making certain other angle theta, then it will have an in between value, which will be given by this in vector terms and this expression in scalar terms. Okay. Now, if we move on from this equation again, r equal to this is equal to r into p sin theta. But what is p sin theta? P sin theta is p theta, right? So we can write L equals to r p theta. That is the tangential component of linear momentum, which in other words means that the radial component, which is along the radius vector PR, that is p cos theta, does not contribute towards the angular momentum at all. Only the tangential component is what will contribute towards the angular momentum. Okay, alright. Now, if we come back and consider parent equation, that is L equal to P into D, what it means is that angular momentum is the product of linear momentum of the object or the particle or the rigid body and the perpendicular distance between the direction of the momentum and the axis of rotation, right? Which is known as the moment of the given vector. Okay, what is the physical significance of this angular momentum? Now, if you remember, in the chapter about Newton's laws, we had defined momentum and we said that momentum is a measure of the motion of the body. When we said motion, we actually meant the translational motion, that is moving from one point to another in straight line or some other path. Similarly, when a body's motion has a rotational part or is in a rotational motion, when a body is in a rotational motion, angular momentum will be the counterpart of momentum, which in other words means that angular momentum is a measure of rotational motion of the body. Now remember one thing, that angular momentum for a given velocity or given linear momentum will depend on the perpendicular distance of the momentum vector from the axis of rotation, which means for longer distances for the same velocity the angular momentum will be higher and for smaller distance it will be smaller. Okay, this is very important. In rotational motion what we have seen is that distance from the axis is very, very important, and that is why we always have expressed the important terms in terms of the distance. For example, in my previous videos when we talked about torque, what we said is that torque is the moment of force, and we said that the torque, that is the rotational effect of a force, depends on the not only on the magnitude of the force but also how far it is acting from the axis of rotation. We had given the example of a door. If you push the door very close to the hinge, then it will rotate less. If you push towards the other edge, from the farthest edge from the hinge, then it will be easier for you to open the door, right? All these things means that in rotational motion, the perpendicular distance or the moment part is very, very important. And that is what this perpendicular distance or this length has been given the term moment arm. Now, the effect of a given physical quantity or the magnitude or value of a given physical quantity, rotational physical quantity like angular momentum, like torque, depends on the length of the momentum for a given force or equivalently for a given linear momentum. So, we have just found that angular momentum vector is given by the product or cross product of radius vector and the p vector, that is linear momentum vector. Okay, so since it's a vector, we can always express it in terms of its components. So we can say that Lx I cap plus Ly j cap plus Lj k cap must be equal to x I cap plus y j cap plus j k cap, and the cross product with px I cap plus p y j cap plus p z k cap. If you undertake the cross product with forming the determinant and finding the values, what you will find is that I cap multiplied by y pj minus j py plus j cap multiplied by z px minus xpz plus k cap into xpy minus ypx, or the x component of angular momentum will be given by y pz minus z py, y component will be given by z px minus x pz, and z component will be given by x py minus y px. Okay. Now, once we have found this will be used in certain problem solving, which we'll do a little later. However, if we come back to the first equation again, that is L equal to R cross P. Now, if we differentiate this equation, what we get with respect to time? dl by dt must be equal to dt of R cross P. Okay, so this will be equal to dr by dt cross P plus R cross dp by dt. Okay, this will be equal to dr by dt, we know is given by velocity vector, cross P equal to mv, mass into velocity, plus R cross, what is dp by dt? Rate of change of momentum is known as force, right, from second law of motion, so this must be equal to F. Now if you consider this part, we can take m outside and we will have v cross v plus R cross F. Now what is v cross v? Our cross product of a vector with itself will give us a zero vector, right? So we can discard this term, and so we will have dl by dt equal to R cross F. So if we say rate of change of angular momentum will give us the torque, right? This is equal to torque. As we have found in Newton's laws that dp by dt was equal to force. So when we differentiate the linear momentum, we get the cause of the change of linear momentum, right? Which is the force. Similarly, if we differentiate the angular momentum, we get the cause of angular momentum, that is the torque. So it will simply mean that for tau equal to 0, which means if there is no external torque on it, from this equation we get dl by dt will be 0, giving us L will be constant, which means that for an isolated system, which means for a system where there is no external torque acting on it, the net angular momentum of the system must be conserved. Just was the case when for f equals to 0, p is equal to constant. Linear momentum was conserved if there was no external force. Similarly, for rotational motion, if there is no external torque, then the angular momentum must remain conserved. Its total angular momentum of the system will not, of an isolated system, is not going to change. This is principle of conservation of angular momentum, which is going to be applied in a very fields in physics in the coming chapters. Okay.